Hi, my name is Sabrina Montserrat, and today I'll be talking about tessellations. So a tessellation is the pattern resulting from the arrangement of polygons to cover a plane without any gaps or polygons overlapping. Tessellations are created by performing one of three transformations on a polygon: a translation, a rotation, or a reflection. Now, even if you've never heard of the word tessellation before, you've still likely seen them in real life. So if you've ever thought about any sort of instance where you saw a repeating pattern like displayed on the slide now, those are examples of tessellations. So you can think about maybe brickwork or stone patios, stone decorative patios, mosaics even, and like bathroom tiles. So these are all examples of tessellations. There are three types of tessellations: regular tessellations, semi-regular tessellations, and non-regular tessellations. Today, I'll only be talking about regular tessellations, but if you're interested in our discussion, I highly suggest you checking out the latter two. Now, regular tessellations are made up of congruent regular polygons that meet vertex to vertex, and regular means that the sides and angles of the polygon are all equivalent. Congruent means that the polygons that you put together are all the same size and shape. The second condition is that the interior angle of a regular polygon must be an exact divisor of 360 degrees, and you'll find that with these two conditions, you can only make regular tessellations with equilateral triangles, squares, and regular hexagons. Now, if you're still struggling with this definition, don't worry, because I'll show you in Geogebra why this works. But if you're a teacher and you're interested in introducing tessellations to your own classroom, these are the relevant Common Core standards I found. But I believe that tessellations are interesting for students of all ages who are learning about geometry. Now let's go into GeoGebra. And I've already prepared this worksheet. And I also added a quick summary of the definition of tessellations and regular tessellations that we can refer to later. Now let's begin with a square. So a square is inherently regular because all of the side lengths are equal, as you can see, and all of the interior angles are all 90 degrees. Now, I said that there were three ways to make tessellating patterns. So let's talk about those now. So if I go down to GeoGebra's transform tool, let's begin with a reflection. So I can start creating a tessellating pattern by reflecting our first square over any of the line segments displayed here. So I can reflect it over this line segment, and it will create a congruent square to our first one. I can also rotate around a point to create a tessellating pattern. So if I maybe select this point and select, oh, if maybe I select it in the right order, it'll work. Oh, let's try that again. I'm going to select our original square, and I'm going to select one of its points, and I'm going to rotate around the point by 90 degrees. And I'll add another square at this area. And the last way I can do it using transformations is to translate it. So if I select our original square and I can create any sort of vector in any direction, let's put it like here if I wanted to. Now this doesn't constitute as a tessellation because our square does not meet vertex to vertex. So in order for that to happen, I need to place it in such a way that the vertices of this square meet any of the vertices of the square I already began, of the tessellation I already began. So I can place it here if I wanted to. And that's what meeting vertex to vertex means. Now, when you're using a dynamic geometry tool, as like GeoGebra, you can also use a regular polygon tool to automatically have it create congruent squares for you, or congruent polygons, whatever you're working with. And since I selected the two vertices, this blue square meets vertex to vertex with our original one. And as you can tell, if I continue this process and I repeat it over and over again, say like I wanted to do maybe here and here, I can create, that doesn't count because it overlapped, and it'll do that sometimes, but I can create a tessellating pattern using any of those methods. Now if I delete everything, because it's going to get a little crowded in here, and I toggle this button, I already went ahead and created four congruent squares that surrounded this point B and shared this vertex B. You'll notice that There are no gaps and there is no overlap between the squares because 90 is an exact divisor of 360. So 90 goes into 360 exactly 4 times, and that's why there are exactly 4 congruent squares around this vertex B, and that's why there's no overlap and no gap. And a similar argument can be made for equilateral or regular triangles. So this triangle is regular or equilateral because all of the side lengths are equal and all the interior angle measurements are equal. So the interior angle of a regular triangle will always be 60. And in the same manner as I began creating that tessellating pattern for the square, I created uh, the start to a tessellating pattern of equilateral triangles that surrounded this point G. Notice also here that there are no gaps and that there is no overlap. The reason being is that 60 is an exact divisor of 360. So 60 can evenly go into 360 6 times, and that's why there are 6 equilateral triangles that surround this vertex G. And if you squint really hard, and you just look at the outer edge of these triangles, you'll see that this is actually a hexagon. So if I overlap the hexagon that I created before, this hexagon is congruent to the polygon that these 6 equilateral triangles create. And since 120 is an exact divisor of 360, in the same way 60 is an exact divisor of 360 and 90 is an exact divisor of 360, I can start to create a tessellating pattern because 120 evenly goes into 360 3 times. So I can place 3 hexagons so that they all share this one vertex T. And 120 3 times adds up to 360. And that's why I can begin creating a tessellating pattern. And if I wanted to, the easiest way to add to this is to use the regular polygon tool to add as many hexagons as I so please. Doesn't matter how many you add, but no matter what you do, if you have a regular square, a regular triangle, and a regular hexagon, you can always make a regular tessellation. Now, I focused on the idea that you can only make regular tessellating patterns from these 3 polygons because they all have interior angles that are exact divisors of 360. Now let me show you what happens if the interior angle is not an exact divisor of 360. So on this worksheet, I copied the definition over to make it easier for us to reference. But I have a pentagon and a decagon. These are both irregular polygons. So all of the length measurements are exactly equal, same with the decagon. And all of the interior angles of the pentagon are equal, and the same can be said for the interior angles of the decagon. Let's start with the pentagon first. So I began implementing the first condition by creating regular congruent pentagons that met vertex to vertex with my original one, but you'll find that gaps and overlapping will occur. The reason for that is because 108 is not an exact divisor of 360, and for that reason you cannot create a regular tessellation because no matter how I place the pentagon's vertex to vertex, I can never fit a regular congruent pentagon in the space. And if I try to, the pentagons will overlap with one another. A similar argument can be made for this regular decagon. So no matter how I place these congruent decagons, there will always be either overlapping or there will always be gaps because 144 is not an exact divisor of 360. And in summary, if an interior angle of a regular polygon is not a divisor of 360, then it cannot make a regular tessellation. Now, I said earlier that there were 3 types of tessellations. So I only talked about regular tessellations, but even though pentagons and decagons can't make a regular tessellation, you can create other tessellating patterns with them. Now, I don't have the time to go over those other 2 types, but if you would be interested in doing more research on your own about them, I think tessellations are really, really cool. They're really fun and interesting. And if you Google tessellations, all these different patterns will pop up. And I just think that tessellations are really cool for students of all ages to learn about. So thank you for taking the time to watch my video. I hope you have a wonderful day. Bye.